Okay. So cosmology. This is the first time I've taught this. Well, I mean, it's the second time I've taught this class, and we didn't do this topic last spring. Um, so I was kind of thinking like, okay, what are the big? I mean, no pun intended, right? Cosmology. What are the big things that you need to know about cosmology? So starting with the expanding universe, but I kind of want to start with big principle. The cosmological principle, right? So I've condensed it into the you ain't special, right? So if that's the one thing that you can remember in about cosmology, what cosmology tells us about our place in the universe. What do I mean by that? Well, okay, so another term for this that I've seen sometimes is the Copernican principle, right? So Copernicus, what did he tell us? Well, okay, first of all, the world doesn't revolve around you. Now, I don't think that, you know, in the time of you know, the Renaissance and the Middle Ages, people didn't really need to be told that, right? Most people, like, their life was just trash. So they knew that the world didn't revolve around them, but, you know, in our comfortable 21st century, sometimes we need to be reminded of that. We are not necessarily the main character of reality. But what Copernicus really said is that the Earth is not the center of the universe. Now, he said the sun is the center of the universe. Okay, neither is the sun. Okay, so then they're like, yeah, all those other stars out there that we can see individually, those are other suns, right? So they're just as valid, and, you know, maybe they have planets. As we know now, lots of them do have planets. But, you know, we could see that there's some large scale structure, right? You can, if it's dark enough, you can see the Milky Way. Eventually people realized the Milky Way was made out of a bunch of stars. But then eventually people realized, well, some of those little smudges out there, like Andromeda, those are whole other galaxies, right? So the Milky Way galaxy is not the whole universe, and it's not the center of the universe, right? So in fact, there is no center of the universe. Now that's the part that gets hard to imagine. And on large enough scales, no matter where you look, the universe looks the same everywhere. Right now, of course, on small scales, this is not true, right? The universe, my universe, is very different room to room, and of course, in the solar system, right, it makes a big difference whether you're on a planet or not on a planet. You know, if we look out, we can see, well, there's clumps of stars, right? So the clumps are very different than the empty, you know, intergalactic space. But on big scales, above the size of galactic clusters and our local supergroup of galaxies, right? So we're already unfathomably huge. That's just, it's all the same everywhere you look. And it looks the same in all directions. We can say, well, at least our universe is the only universe. Well, maybe. That's hard to say, right? So we're not necessarily gonna go there. Well, you know, then this would be different from the many worlds interpretation of quantum mechanics. But the other thing that is, you know, when we say the known universe, it means the region of our universe that we can see, right? So we can see, you know, 14, 15 billion light years in all directions, and that is symmetric, right? So it kind of looks like we're in the middle, but that's just because that's what we can see, right? It would be like going out into, like, you know, the middle part of north central Indiana, right? So, like, I don't know, north of Kokomo, south of South Bend, where it's just corn everywhere, right? Or soybeans, right? If you look in all directions, the horizon is equidistant in all directions, but that doesn't mean you're in the middle, right? That's just the edge of what you can see. So that's kind of our experience in the universe, right? The edge is the same distance in all directions, but that's just, you know, our field of view, right? It doesn't mean we're in the middle of it. Okay, so that's our guiding principle, and we'll see observations that demonstrate this, but it's also sort of a guiding principle. You know, if you ever see something that makes us look special, you kind of have to say, like, okay, why is that not, you know, why is that sort of an accident and not, not an actual evidence that we're special. So that's sort of, you know, our null hypothesis, right? I'm willing to accept somebody finding proof that we really are the center of the universe, but they're going to have to prove it, right? We can't start with that assumption. Okay, so, well, what are our observations about this? So the one of the big observations has to do with the Doppler effect, right? And you know, I found a physics textbook that was explaining the Doppler effect, and it was like, it started out saying like, you know, students these days, and I don't know when these days was, but they probably, you know, don't have as much experience being around trains. And I was like, well, okay, this does not apply to Indiana State, right? We all hear the Doppler effect when we're on campus multiple times a day, right? So it's the train whistle, right? As the train's coming towards you, it sounds higher pitch, and after it passes you, it sounds lower pitch, right? You can hear this with car sirens, or even just the sound of a car engine. If you go to the speedway for the Indy 500, right? Especially when there's a single car on the track, you really hear the sound, right? That's the Doppler effect. So that's something that we're familiar with waves, right? And what really happens there is, you know, you can think of a wave as being, you know, it's got peaks and troughs, right? And the wavelength or the frequency depends on how far apart they are, right? So if something's coming towards you, it's gotten a little bit closer by the time, you know, if it emits one peak, it gets a little bit closer to you by the time it emits the next peak, right? And so that effectively scrunches the wave together, right? And then if it's going away from you, it's going to be a similar effect, right? It emits a peak and then gets a little bit farther away from you before it emits the next peak, so that stretches it out. Okay, so that's sound waves, but light waves would work the same way, right? And you know, it might be even easier to visualize like a water wave, right? If you're moving, you know, if there's like something bobbing up and down, producing waves, and you're in a boat that's going toward it, you're going to hit those peaks of the wave more often than you would if you were just sitting still, right? And if you moved away from it, you'd feel them less often. Okay, so with light, it's a similar thing. It's just that the velocity needs to be close to the speed of the wave, close-ish, at least on a similar scale, before you can actually notice it. So we don't notice a Doppler effect with light in our everyday life because things don't move near the speed of light, right? So we skipped over this when we did the special relativity chapter, but it's a very similar analysis. Right, so this simulation here is looking at light. Is in the so there's a source that's moving to the right at 0.7 times the speed of light, and it's emitting a frequency in the middle of the visible spectrum, so about green. Right, so you can see that if you're on the right side of the picture and it's moving toward you, you'd see that light. We call it blue shifted because, I don't know, violet always, you know, tends to get the shaft in these. You know, we talk about red versus blue. So it's blue shifted, right, because the wavelength is decreased or the frequency goes up. And if you were on the other side where it's moving away from you, then it's going to be red shifted. And if you're at an angle, it gets a little bit more complicated of a calculation, but similar sort of idea. So if something is moving toward or away from us, and we know what frequency of light it should be emitting, we can figure out what its relative velocity is to us by seeing how red or blue shifted that is. So that's the special relativity. That's the things, you know, moving within space. But as we'll see later, what if space itself actually expands, which is also happening on large scales. So if space itself actually expands, well, the calculation's much easier, right? The wavelength of the light or whatever is emitted is just going to be stretched by however much space stretches. So if space is stretching, then everything's going to get redshifted. just because this, from the time that the light is emitted to the time that the light gets to us, space itself has stretched out. There's not really a good analogy for that in, you can't really make an analogy to sound or water waves with that. But this sort of picture of something on a rubber band kind of gives you that idea. Right, so both of those effects happen. We'll see that one is more important than the other in the cosmological scale. Okay, so with that sort of in mind, we can start looking at space, looking at stars, and make a measurement of how fast they're moving toward or away from us by looking at their spectra. Right, so stars are black bodies generally, so they have a continuous distribution in the spectrum, like we calculated whenever that was, a week ago, looking at the black body radiation with bosons. But they also have atomic elements within them, right? So the atomic elements are going to absorb light at certain specific wavelengths that correspond to the energy levels in that atom, right? So this is also how we can tell by looking at stars, whether they're mostly made of hydrogen, helium, oxygen, right? Because we can just on Earth, we can use the Bohr model to calculate what those should be, but on Earth we can also just like heat up a gas of hydrogen and see what the spectral lines it emits are. Right, so here you see the line spectrum of the element. That would be the emission spectrum. That's the same. Those would be the same wavelengths as what the gas would absorb if it's in between us and the light source. So you just look at that spectrum, find the absorption lines, and you see that they get shifted one way or the other. Now this is a overly dramatic representation of what you actually tend to see, but it's with precise measurements you can get a good measurement of that red or blue shift. Okay, so Hubble's observation. So this is Edwin Hubble, the person, not the Hubble Space Telescope. I didn't write down that this was the 20s. So he and his students, they made these measurements for a variety of galaxies. So, and then he plotted the velocity, right? So here, positive means moving away from us, and negative would be moving toward us, as a function of distance. So, okay, you can see that this is not one of these ultra precise measurements, right? This is a scatter, and he did a line of best fit. And he found that the farther away a galaxy is from us, the faster it's moving away from us. Now, this part down here in the near zero, right? The nearby galaxies, some of them are moving toward us, right? So the Milky Way galaxy is moving toward Andromeda galaxy. They will eventually run into each other. We got other problems to worry about before then, like the sun dying and stuff like that. But eventually this will happen and the galaxies will rip each other apart. So nearby galaxies can be moving toward us, but the overall trend is that they're moving away from us. Now, I'm going to show you the distance scale on the bottom is in megaparsecs. Parsec is, there's some weird definition to it that I can never remember because I'm not an astronomer, but a parsec is 3.26 light years, right? And so a megaparsec is 3.26 million light years, right? So it seems pretty far away from us, right? And we also see that the recession velocities are, in hundreds or thousands of kilometers per second, right? But on big scale of the universe, if they're 3 million light years away and they're only moving 100,000 kilometers a second. It's not like, you know, there were galaxies that Hubble could see that we can't anymore, all right, or that look small because they're moving away. Big time scales, big distance scales. Okay, that was convincing enough, right, to define this this line of best fit. You know, Einstein actually, when he solved his general relativity equations, found that the universe should be expanding or contracting, but he didn't really like that, and so he just threw in a fudge factor to make it stable, and he later called it his biggest regret. But because he's Einstein, it actually turned out that that cosmological constant is important, as we'll see later, and in some sense is really there, although it doesn't have the effect that he thought it should. So here's an update, right? So there's Hubble's original data in the lower left, and you can see that little red square in the bigger plot. That's where his data would all fit. So nowadays, so these are these observations are much more recent, over the later part of the 20th century, and you can see that the line of fit is much better, right? Although, you know, within his error bars, you know, our measurement is still within his published error bars. So, you know, he didn't have as solid of data. It looked a little bit more scattered, but we're still in general agreement with his measurement. Now, another thing that I want to point out here was that you can see here it says for type 1a supernovae. So that's a Roman numeral 1A. So there's various types of supernovae, and this is the supernova of a white dwarf. And they are used as what's called a standard candle, because these types of supernovae are very consistent in their brightness. So they're very consistent because there's really only one mass that a white dwarf star can have and go supernova. So they're very consistent. So you know, there's always this problem with astronomy, right? Is that thing really far away, or is it just naturally dim, right? Because the farther away it is, the dimmer it's going to look, you know, keeping that standard. So if you have this standard candle of the type 1a supernovae that you know what its actual brightness is, you can figure out its distance based on how bright it appears, right? So that's very important. And so Hubble didn't have that, right? He was just looking at brightness of galaxies and trying to estimate from that. So that's another reason why his error, well, I don't know. I'll take some points off on this graph for not showing error bars on the distance to the galaxies. I don't know if that's Hubble's fault or just the website I got it from. But here you can see they put error bars on the distance, but the error bars on the velocity are very small because, you know, we can do a really good job of measuring the redshift, right, based on the spectral data. So anyway, we see that same linear fit. So we can put that into Hubble's law, which I don't know if I made this up. I don't know, it just kind of came to me, but I can't swear that I didn't read it somewhere else before. The farther it is, the faster it flees, right? This, I don't know, it's kind of inspired by what my dad told me in Little League. The faster they throw, the farther it goes if you hit it. It didn't really work for me, though. I was never that good at baseball. Anyway, maybe it's because I needed glasses. Never got them until I passed the ball to the cheerleader in 7th grade. Then I was like, okay, I'll get glasses. Okay, in basketball, not in baseball. Okay, so the faster it is, the farther it flees. So here's Hubble's law. Velocity is proportional to distance, and there's this constant, h naught, the Hubble constant. And so our measurement for the Hubble constant is 72 kilometers per second per megaparsec, plus or minus 4%. Right, so there I have the definition of parsec in light years and kilometers. So if you look at that, you've got a velocity divided by a distance. So that gives the Hubble constant a value of 1 over time. So if we flip that over and say, well, what's the inverse of the Hubble constant? It's going to be a time, 14 billion years, which we can interpret as the age of the universe. Right? So you can basically say, well, the farther away it is, the faster it's going. So if we turn that around, how long would it take to make everything come back to the same place, which would be the Big Bang? And so this is 14 billion years. That's our best estimate for the age of the universe based on this this expansion and the value of the Hubble constant. Okay, so hold up. Right? If we look everywhere we look, things are moving away from us. Right? And this took me, I mean, as I've said, I was a nerd, still am, I guess. So I would read I'd get these books on physics from the library, in middle school or whatever, and they're like, everything's moving away from us, so that's evidence that there is no center to the universe, right? And if you went to some other galaxy, they would also think everything was moving away from them. But we haven't been to another galaxy to look from there, right? I mean, the farthest probe that we've ever sent is just now leaving the solar system, and it's not designed to like look at redshifts or anything like that. So that's not, we get a bigger change in perspective from just orbiting around the Milky Way, right? So how can we make this claim, right? Why isn't this evidence that we're the middle and everybody's running away from us? So, okay, maybe we are special. I mean, maybe especially annoying, and everybody's trying to run away from us. But remember, the key point was the faster it is, the farther it flees, right? So if you just like, I don't know, juvenile example. So if you're like in a large crowd and you just fart, right, and everybody wants to get away from you, right? Everybody's going to move away from you at their walking speed, right? So the person who's 10 feet away from you is walking away from you, and the person who's 20 feet away from you is also walking away from you. So they'd be moving all at the same speed. But that's not what we see. We see the farther away things are, the faster they're moving away from us. So this picture here on the left is, okay, just imagine like, put a grid of points everywhere in space. If everything expands uniformly, right? The distance between, okay, so it has D1 there, right? D1 is going to multiply by some constant, K. And D2 is also going to multiply by that constant, K, right? But D2 started out bigger than D1, right? So the change in distance is going to be bigger for the part that started out, for the point that started out farther away from us, right? So it's not like we're just in a room and an open field and everybody's moving away from us. It's that everybody basically feels like they're in the same point in the field, but the field is stretching, right? So there's all these analogies that people try and come up with because like our tiny brains can't imagine space stretching very well, right? So you get this picture of, well, if you draw a bunch of dots on a balloon and you inflate the balloon, right? All the points on the balloon are going to all move away from each other, and the points that are farther away will move away faster, right? But I don't, that gets a little confusing because like, okay, the balloon definitely has a center, right? That's in the inside, but you have to imagine that the middle of the balloon is not part of the universe. That gets tricky, right? I mean, I guess it's not that tricky. We live on the Earth, right? We don't normally think about the the inside of the Earth as being part. Like nobody lives there, right? Another place where Hubble's law applies is banana or blueberry bread. Right, so if you put blueberries in your batter, they all have a certain distance apart from each other, and then they more or less move as the batter expands when you bake it. Yeah, would it be batter? I guess it's a quick bread, not a dough. Whatever. Um, so this is appropriate for our times with all the stress break baking that everybody's doing. Um, Maybe chocolate chips, whatever your choice may be. Again, the visualization is tough because there is still a center, right? And also because the ones near the bottom of the pan don't actually move. Hubble's law still applies, right? The farther away they start, the more they increase in distance. But it's hard to picture this space expanding everywhere in all directions, and the question of what it's expanding into is just meaningless because there's nothing outside of space, right? So oh, there's somebody else's dog. um, so yeah, it's really hard to wrap your mind around, but I think I've mostly gotten there, right? And so the thing that I like to say, when people say like, where did the Big Bang happen, or when did it happened? Everywhere all at once, right? It's just that everywhere was a lot closer together back then.
I have a question.
Yes.
Does that mean there's things we're moving away from things as well? Like we're not the very like the edge, right? Like we're just part of this. I don't know
Right.
how I'm visualizing it, but like I imagine stuff behind us that we're moving away from too.
Well, so it's relative, right? So from our perspective, everything is moving away from us, right? But if you went to Andromeda and looked in all directions, you'd say everything is moving away from us there, right? So, we look in all directions. We see Andromeda going this way. We see uh, M81 going that way. I don't even know if that's accurate in the directions. I think that's a galaxy. Whatever. Um, we see these things moving in opposite directions, right? But if you go to the galaxy that's over here, Andromeda, they would see us moving away, and they'd see, M81, if it is on this other side of us, moving away from them even faster, right? So if we look in all directions, like it's the horizon thing, right? We see we're in the middle of, the horizon is equidistant all the way around, right? Um, So, take that analogy of northern Indiana, right? If you're in Tipton and you look in all directions, you say like Tipton's the middle of your field of view. But if you go to Plymouth, uh, you would also say, okay, I can see whatever it is 30 miles away in all directions from Plymouth, right? So, I said there is no center. The other way of looking at that is every point in the universe is equally valid to be able to say that they're the center, right? It's kind of like it's not exactly the same, but it's kind of like in special relativity, you would say, each of those spaceships is able to say, I'm at rest, you're moving, so I see your clock running slow, right? So everybody in the universe sees everyone else moving away from them.
It's just whatever your frame of reference is.
Right. So all those frames of reference are equally valid. Right. So I guess, I don't know. You could take it from you're not special to everyone's special, right? Every galaxy gets a trophy, center of the universe. Yeah. Now, of course, that doesn't the forces that are holding things locally together are bigger than the expansion, or they overcome the expansion of the universe, right? So like my table's not growing in size because the universe is expanding, right? Because the forces holding it together they hold it, they keep that expansion of space from pushing things apart. Or like the solar system, right? The gravity of the solar system, or the gravity of the Milky Way, or even the gravity of our local cluster of galaxies keeps those things relatively held together as the universe expands. And so that's why some of those local galaxies are actually moving toward us. But as you get to bigger and bigger scale, gravity drops off, but the expansion of the universe still is there. And so those, the farther away things are, the more they'll be expanding. So you could imagine, well, we'll talk, about the fate of the universe later, but you could imagine if this continues indefinitely, at some point, you'll get to the point where we won't be able to see any other galaxies, right? They'll all have been pushed away, or at least we won't be able to see beyond our local group. Okay, we need further evidence, right? So this is a true story. So Penzias and Wilson, 1963, they were just trying. They had a microwave telescope, and they were just trying to see, like, okay, what's our background? What's like dark sky, right? And so they were looking at a certain wavelength, 7.35 centimeters, which is in the microwave range, right? Because they're a microwave telescope, and they just had this. I mean, well, they were kind of listening to it, or you could, however your output is. They called it like a hiss, right? So, okay, where's that coming from? Is it a nearby city? No, if we point our telescope over here, we still get it right away from the city. Is it, they thought maybe, nuclear tests. Well, those should fade, right? If there was a nuclear test recently, then it should eventually fade away. Okay, it didn't fade away. They thought maybe it was from the Van Allen belts, which are trapped ions in the upper atmosphere that are responsible for the aurora, northern and southern lights. But that fluctuates over time, and they didn't see fluctuation. So then they looked up in their telescope, and they were like, okay, there's this pair of pigeons there nesting, pooping everywhere. So they got they trapped the pigeons, released them somewhere else, cleaned it up, still saw this microwave hiss. So eventually they were like, okay, well, what would the temperature be? Well, if we measure the power at that wavelength, if we assume a black body spectrum, we can measure the power at any wavelength. It doesn't necessarily have to be the peak, and we can determine the temperature of that black body. So they measured it to be 3.1 plus or minus 1 Kelvin. It was later determined that this is basically the afterglow of the Big Bang. And for this observation, they were eventually awarded the 1978 Nobel Prize in physics. So what do we mean by afterglow of the Big Bang? Well, we kind of have talked about the epochs of the universe when we were talking about Big Bang nucleosynthesis, right? So, first it's too hot for even protons and neutrons to form, but then they form, and then the first nuclei can form of hydrogen and helium, right? And so then as things are cooling down, okay, so you still, even after you form nuclei, it's too hot for atoms to form, so you just have this plasma, right? And a plasma is generally going to be opaque to radiation just because you have all this charge flying around, right? I mean, it's overall neutral, but there's positive and negative charges everywhere. So any photons are going to be scattering off of all of this hot, dense plasma. Then as things continue to expand, then you start to form atoms, right? The electrons become bound to the nuclei that have been formed. And at that point, then I think there's still, it's still very hot, so it's opaque to radiation. But at a certain temperature, the gas is diffuse enough that most of those photons that have been bouncing around will no longer scatter, right? They can just fly freely. So that's called the time of last scattering, right? And so most photons in the universe, or at least a large number of photons in the universe, have been just freely flying throughout the universe ever since that time shortly after the Big Bang. So whatever the temperature was at that time, they had a certain wavelength, right? And it's going to be a distribution because it's a black body spectrum, but it has a certain, they have a certain wavelength. But as they've been flying to get to this telescope in 1963, and still continuously now, the universe has been expanding, right? So those wavelengths, which started out fairly short, have been stretched so that they're all mostly in the microwave spectrum now. Right, so they measured at this particular wavelength and were able to determine their best estimate of the temperature of that we call the microwave background radiation, or the cosmic microwave background radiation. Right, and they found that it was uniform in all directions. Okay, so so how were they able to determine the temperature? Right, so let's look at that calculation. So this is I'm showing this all on one line because this is something that we did last week for the black body spectrum, right? So so basically we want to figure out how can we compare the temperature of a single photon and figure out a temperature from that, or any given photon. I guess the average temperature, the average energy of the photons, right? So we, as always, start with the integral for number, or number per unit volume, right? So we have that density of states. We have the Bose-Einstein distribution, right? Factor out the dimensionful stuff, and you get that dimensionless integral, the one that gives you something weird, doesn't involve pi, right? And so we get this, combine all those constants. Okay, so we find that the number per unit volume depends on temperature cubed, right? So how many photons would you have in a given volume? It depends on the temperature to the third power times this constant, right? So so basically for each degree Kelvin then cubed, you would get what is that? 20 million photons per cubic meter. Then we can also calculate the overall energy, right? So we did that again last week. We found that the energy is this mess of constants again times temperature to the fourth. Right, so if we take that energy and divide it by the number density, right, that's the energy of all of the photons, divided by the number of photons per unit volume, that'll give us the energy per photon, right? So it's just the ratio of those, it's U divided by N over V. So we get this constant 2.33 times 10 to the negative fourth electron volts per Kelvin. Right, so you measure they actually measure the energy per photon, right, and then you divide that by that constant, and that gives you a temperature. Okay, so that's so it's just using this basic black body radiation spectrum. So that's it's a pretty good assumption, but we'd like to measure at all wavelengths, or at lots of different frequencies. And so over the years, people have done that better and better. Right. So here's from the Cosmic Microwave Background satellite, COBE. And I mean, just look at that fit, right? I mean, it passes right through the center of all the error bars over a frequency range of an order of magnitude, right? So this is all microwave, right? So yeah, I don't know, one over centimeters. I don't know, hard to visualize. That's really wave number, not frequency, but whatever. And the intensity is some dumb unit that astronomers use. I remember when I was at McAllister and astronomy majors would give their talks. I'd be like, could you define that? I don't even remember what JY is, and none of them ever could, but whatever. It's a measurement of its intensity of the radiation. So with a much better fit, COBE, this was in the 90s, 80s to 90s, I think. you can see perfect fit to a black body spectrum at 2.7 Kelvin, right? So that's basically the temperature of like empty space, right? The photons that are just there that are left over from the Big Bang. Okay, so great fit, everything looks beautiful. We can look at even better precision. So here's a picture of looking at very tiny fluctuations. So let's start at the top, right? So we're comparing COBE in the left column to WMAP, which was in the early 2000s. That's that satellite. Wilkinson microwave anisotropy, right? So differences, isotropy means the same in all directions. So it's looking for slight fluctuations in where you look, how that changes the spectrum, right? So the top one is in a scale where blue is 0 Kelvin and red is 4 Kelvin, right? So it's basically showing that, yes, overall, it looks very much the same. Now, the other ones have a tighter range. Now, that yin-yang sort of look that you have on both of those, that's because the probe is moving through space, right? And I think the biggest impact there is our rotation around the galactic center, right? So we're moving toward the blue direction and away from the red direction. So you have to subtract that out, right, in order to have a realistic picture. You know, you don't want to. Yes, so that's sort of that that special relativity blue shift red shift Doppler effect, as opposed to the stretching of space. So you have to subtract that out. And when you subtract that out, that's the final picture that you get at the bottom. So in that bottom, the scale ranges from blue meaning 2.721 Kelvin and red being 2.729 Kelvin. Oh, I said that. Yeah, sorry, I said it backwards of which way we were moving, because it's not blue shift red shift. It's hot versus cold. So it's the other way. We're actually moving away from the blue region and toward the red region in that middle column. So you can see that's a very tiny scale, right? You know, a range of 0.008 Kelvin. The big red blob in the middle is because that's the disk of the Milky Way galaxy, right? So that's hard to subtract out because there's just stars in the way, right? So it's really, you know, really tiny fluctuations once you get away from just like, hey, looking at the Milky Way. We can see that there's even better refinements coming. So the Planck satellite, which is up now. So COBE, you know, this is like the same patch of sky, right? COBE, we get a very fuzzy, you know, I don't know, standard def HD 4K, right? As we're going from there, better and better precision. Again, it's still mostly all the same. We're looking at tiny variations, tiny fluctuations. Okay, so our follow-up questions: why is everything the same everywhere? What do the fluctuations mean, and what's the fate of the universe? Right. So, are we going to a big crunch? Are we going to keep expanding the same way forever, or might we expand? Next time, the dark universe decides our cosmic fate. Right. So we got dark things fighting against each other for whether we will crunch or whether we will continue to expand. All right. So sorry, I didn't realize I was running out of time there. So that's for Friday. So any questions, or if not, that's all I got.